Yes. No, thank you. 1:30 maybe, okay? Right. I have something very interesting to show you. Okay, something that might look confusing, but it's going to be very interesting. I posted this on Avenue to Learn. Right? I posted this on Avenue to Learn. So this is so today we are going to go to an example of centric buckling with extended Euler's formula, and hopefully on Friday I can start on eccentric buckling. Okay, so one is centric, the other one is crazy. Right. So I want you to look at this structure now. Okay, and I'm going to draw the transformation. You can find this structure on Avenue to Learn, and I've posted it. Okay. Right. So this orientation over here represents the diagram here. Okay. This diagram here. So we are going to focus on member AB. We are going to focus on member AB. Okay. So member AB is the structure that is under compressive axial loading. Okay. So if I just sketch this diagram now, you have point A and you have point B. And by looking at the diagram, both of them are what? Both of them are pinned. Okay, both of them are pinned. Muchas gracias. One tequila. Okay. Now, if we were to focus on buckling in the XY plane, right? Now we are looking at the XY plane, yes or no? So this is our X. And this is our Y. Sincerely apologize. Can you change this to BC, please? Right? So if I'm going to sketch the deformation pattern due to buckling, it will likely look like this. Agree? Now, both ends are pinned primarily because bending moment at point A or bending moment at point B, do apologize again, is equal to 0. Bending moment at point C is also equal to what? 0. So we know when both ends are pinned, right? Both ends are pinned. So pin on one end, pin on the other end, LE is equal to L, right? This is because pin at both ends. That's straightforward. Okay. Now, if we're going to change our view now, okay? So what I'm going to draw now is draw this view now, okay? So now we're going to sketch this view now. So it's a straight line, okay? It's a gap over here. Okay. And then we have the pin running across. So now this is still my point B, and this is still my point C. So where we are viewing now is this is my X. This will be our Z. And then this is our rotation about Y. I do apologize. Yep. And this will be our rotation about Z. Can you include that, please? So now we are going to focus buckling in the which plane? Anyone? What plane are we looking at now? XZ plane. Are we clear? So when this is the case, right? How this thing is fixed. Now moment at point B is not equal to 0, and moment at point C is not equal to what? 0, right? Because if we have another body connecting here, right? We have another body connecting here, like what you can see at point C and at point B. Along the exact plane, the structure is not able to what? Rotate. Why is not able to rotate? Because there's a resistance in rotation due to the structure over here and due to the structure over here. It's preventing the what? Rotation. Can you all visualize it? Yes or no? I need you all to visualize this. Because if you can't, you will say that buckling along the XY plane and XZ plane is the what? It's not the same. So when this is the case, the structure will deform this way. Okay, I'm going to sketch how the structure will deform. The structure will deform, so it's going to be, because it will deform this way. Okay, and I like to emphasize that it's a straight line over here, and then you will bend this way. Why? When this is the case, our structure is under what? This is known as what? Fixed. And this is known as what? Fixed. So when both ends at fixed, okay, we know that LE is equal to 0.5 L. Okay, so the equivalent length is equal to 0.5. So what has the higher tendency? So for this case, okay, buckling will occur in the XY plane. Okay, and this is because LE is equal to 0.5 L, or L is equal to L, and also dependent on the cross-sectional area. So you have to check. When I say cross-sectional area, is dependent on also your what? Your I value. Are we clear? Okay. Now, did I tell you that I still play with Lego? Yes or no? Have you heard that I still play with Lego? Some of you do, some of you don't. Okay, why do I still play? Have you all played with Lego? Yes or no? Why I still play with Lego up to today? It's not that I have nothing better to do. It's not that I don't love my wife more now. I do. Okay, so why do I play Lego? Anyone? Okay? When you all have to learn how to play. Why? I started building, I love to build houses when I play Lego. Okay? So when you build your house on Lego, what do? You build the base first and then you build the what? The roof, yes or no? And sometimes Lego don't make the type of brick giving me hard time. Oh, the dynamic and static friction, one is higher than one. So seriously, how about the surface roughness change that you don't know you saw? Really, it does not make sense. Things are impossible. Anyway, it's a private matter. Right. So remember when you build Lego, you start from the base and you go up. Then you realize that there's a roof that you design that Lego don't make that cut. Yes or no? So what I did is I got pissed off. I started doing what? Build the roof first, and then go to the base. And I explained this to my friend who is a colleague of mine who is a prof in civil engineering. Hey, Dr. What's his name? Oh, no. Dieter Story, Dr. Story. He's emeritus now. I told him, when I built my house on Lego, I started from my roof. And then when I break down the foundation, it works. You know how did he look at me? Really, Eugene? I said, yeah. That's how civil engineers build their structure. They start from the top to know what's the load at the top, and then they build the what? Are we clear? Moral of the story is what? You have to play, then you will learn better. Are we clear? If you just study and do F all, you're not going to make it. Okay? So shall we stop class now? No, I'm just kidding. Okay? So you need to be able to play, then you discover. Okay? I don't care what grade you get. I want you to play. Don't play jokes on me, yeah? All right. So now you can visualize this. Okay, so let's go back to our example yesterday. Okay, we go back to the example yesterday now. Okay. I'm glad you all get the aspect of design. Okay, that's important. All right. So coming back to yesterday's problem. So you understand how to do a multi-body analysis now, yes or no? Nothing to memorize. All you need to do is apply Newton's what? Third law. Are we clear? Just to quickly recap, we are going to determine the maximum mass at sea that the rod can withstand. Okay. So we drew our free body diagram, and we did our what? Method of joint analysis at point A. So next, we are going to carry out static analysis. So what we are going to determine now, we are going to determine what is, we are going to determine FAB. Okay, we are going to determine FAB. So the first thing we do, given that we know this angle is 60 degrees, this angle over here is 45 degrees. So we are going to have summation about forces in the y direction is equal to 0. So what we are carrying out static analysis. Right? So we are going, so we have, what do we have? Okay, we have FABY, positive FABY. Then we have minus FADY. Then we have minus FAC. The whole thing will be equal to 0. Okay. So FABY, so we know that if I draw in this diagram, this is 60 degrees. And based on vectors, this is 45 degrees. Okay, so FABY is equal to FAB sine 60 minus by FAD sine 45. And then we have our minus FAC, and the whole thing will be equal to 0. So sine 60, 0.866, FAB, minus by sine 45, 0.707, FAD, minus FAC is equal to 0. Okay. So this is our equation number 1. So this is just purely very simple static analysis, as you can see. And then the next thing we do is we do summation about forces in our x direction is equal to 0. So in the x direction, we only have two components, right? So FABX minus by FADX is equal